All right, welcome back, everybody. We are continuing to lay out the framework for, again, that hypothesis testing procedure, at the heart of which is determining if results are what are called statistically significant or not. We've talked about some of the basic purposes of hypothesis testing, and last time we reviewed our different hypotheses, the null and alternative hypothesis. Uh, Today we are going to talk about how we decide whether or not to do what's called rejecting the null. So remember, the entire test revolves around the null. We're either going to reject the null because there's strong enough evidence to throw it out, or we're going to keep it because there isn't strong enough evidence. We stack the deck very heavily in favor of retaining the null and make it very difficult to reject it because we want to have a lot of confidence when we reject it that we are right. We want to have relatively low uncertainty around that choice. So the region of rejection is how we do exactly that. So back here we have kind of an approximation of the normal curve. We're going to talk about what role the region of rejection plays in there. But first, we'll talk about the idea of a significance level. The significance level basically determines how easy or how difficult it is to reject the null. So before you run any tests, you definitely don't want to do this after the fact. Why? Think about it for 2 seconds. If you got to set what determines significance after the test, you probably would set it in a biased way. You probably would set it in a way that would make your results significant more often than you ought to, because people are usually attached to their predictions. So before we run any statistical test, we establish a significance level, what's known as an alpha level. And we see this little kind of sideways fish looking thing that's a lowercase alpha. Alpha is a central part of hypothesis testing. It's at the core of a lot of what we do and how we do what we do in hypothesis testing. So make sure that you are really clear on what alpha is and on what role it plays and how it connects to a lot of the other concepts. So here's what alpha is. Alpha is a probability level. Specifically, it's what we'd call a probability threshold. Basically, what you do is you pick a number, and you say anything that's more unlikely than this number, that's more improbable, it has a lower probability, I'm going to reject the null. Whether it's past the line by an inch or a mile, the decision is the same, I'm going to reject the null. If the result has a probability level that's higher than that threshold, even if it's super duper close, we're going to fail to reject the null. So you could set the alpha level at basically anything. It's arbitrary. It's just something that we make up. You'll never have to pick an alpha level in this class because, again, you could pick any number. There's no right or wrong. It's just where you choose to set it. But conventionally in research, we either set the alpha level at 0.05 or 0.01. In other words, we're only going to reject the null if we see results that have either less than a 5% chance of happening if the null was true, or less than 1% chance of happening if the null was true. Why do we do this? Why such low numbers? If we set higher numbers, it'd be easier to reject the null, and that's what we want, right? Well, no. Again, we want to make it really hard to reject the null because the downside of making it hard to, or the flip side of making it hard to reject the null is that when you do reject the null, you now have a lot of confidence that you made the right decision. Your uncertainty drops. So keeping those alpha levels low sets a high bar. Essentially, it makes it so it's a real uphill climb to reject the null. We need a really compelling pattern of evidence. This means, again, that our results are less likely to be wrong when we choose to reject them, because there's a lower probability they could happen due to chance. That probability is never zero, however, so you never get all the way there. So here's a good way of translating an alpha level of 5, basically saying we're going to conclude that the differences we observe between the means we're comparing are meaningful if there is a 5% or less probability that they were due to chance. That's all that it's really saying. Results that have less than a 5% chance of happening due to a fluke, we're going to conclude, hey, there's something going on here, we're going to reject the null. 0.01 is exactly the same thing, but plug in 1% probability instead of 5. So if the probability of our result is less than alpha, or if it's right on the line, that never really happens, but it's possible, or if it's right on the line, then we reject the null hypothesis. We have what's called statistical significance, which occurs when the pattern is so compelling, the differences between the means we're comparing is so big, that it's very unlikely to be a fluke. If your probability of your result is greater than alpha, even if it's super duper duper close, we don't reject the null. So here's the thing. Sometimes people have been keeping up with the plot a little bit better. At this point, they'll say, is there really a meaningful difference between a result that has a 4.9% chance of happening due to chance, which would be significant, and a result that has a 5.1% chance of happening as a fluke, which would be non-significant? No. It's an arbitrary line. It's a line in the sand. There's nothing magic about 5% or 1%. Those are just round numbers that people find easy to think about. As my old stats professor used to say, R.A. Fisher, who was a super prominent statistician about 100 years ago, R.A. Fisher woke up one morning and said, 1 in 20 is good enough. And everybody said, that sounds reasonable, R.A. You know this stuff better than we do. So basically, it's a deliberately simplified decision just to, again, turn those tests into binary yes or no decisions. We'll talk about some of the downsides of that later on, but one main advantage is that it's simple. If we fail to reject the null, we have what's called non-significance. Sometimes we write the little letters NS. This means there could be a significant difference there somewhere, but we didn't find compelling enough data to observe that. So here's how that alpha level ties into our results. Okay, let's say this is a normal distribution. And let's say that this normal distribution represents every single outcome we'd be likely to see if the null was true. So if the null was true, sometimes we'd find sample means drawn from that population that are really close to the mean. Once in a while we'd find them a lot farther away though. They'd be either far above or far below the mean. So the farther away you get from the mean, the less likely those results become if the null is correct. But again, that probability is never zero. We use the alpha level to designate portions of this distribution, especially unlikely portions, as meaningful. And we say, okay, alpha is 0.05, right? So 0.05, there has to be less than a 5% chance that these results are a fluke for us to reject the null. The way that we represent that here is we say the most extreme 5% of scores, the most unlikely ones, the scores that are really far below average or really far above average, in that most extreme 5% of those outcomes, that's going to let us reject the null hypothesis. So essentially, what we might do is we draw kind of a line, and we say, okay, any result beyond that line has a lower chance of happening than alpha. Anything that's beyond this line has less than a 5% chance of occurring. So what we're going to do, any sample mean that falls in that area, we are going to choose to reject the null because it has a lower probability than that alpha level that we designated. Anything that's not in that shaded area, that's not beyond the threshold, it has a higher probability than our alpha level. So our decision is I apologize for my handwriting, but I'm just glad I'm not knocking it over at this point. Our decision is do not reject. So here's the next thing that we consider. The size of that region of rejection is determined by alpha. If alpha is 0.05, then this shaded area would be 5% of the distribution. If it was 0.01, that would be 1%. But the next thing we need to figure out is whether or not we want to look at the most extreme 5% only in one tail of the distribution, or if we want to look at it in both directions. And if extreme scores in both directions from the mean will allow us to reject the null. So remember how we mentioned in the last video that there are 3 possible alternative hypotheses. Again, we have a non-directional hypothesis, which just says there's some kind of a difference between the population means, but we don't say what. Then we have 2 directional hypotheses. Maybe mu1 is less than mu2, maybe mu1 is greater than mu2. And we talked about how that affected the alternative and the null hypothesis. Well, that first one, that non-directional hypothesis, calls for what's called a two-tailed test. We need to be able to reject the null based on that if our sample mean is really far above average for the population we're comparing it to, or if it's really far below average. So what we do in that case is we construct what's called a two-tailed test. Our region of rejection, the area where we will reject the null, is split in half. So now we can reject the null if there are scores that are really far below average, or if there are scores that are really far above average. Now we have 2 areas of rejection. Here's the thing about those areas of rejection. The overall size stays the same. It's still the most extreme 5% or the most extreme 1%. How does that work? If it's a non-directional hypothesis, you split that region of rejection in half. So now, if it's the most extreme 5%, but we're splitting it in half, the lowest 2.5% and the highest 2.5% will allow us to reject the null. It still adds up to 5%. So when the region of rejection is split among the 2 tails, it's a little smaller in each specific tail because instead of the most extreme 5% all in one tail, It's now the most extreme 2.5% in each of two tails. So the threshold, the edge, the border of that region of rejection gets a little farther away. If we have a directional hypothesis, though, we would just have a one-tailed test. Say that we were only interested in scores in our population mean being above average and mu1 being higher than mu2. If that's the case, then we would have no region of rejection here on the left side. So even if you found a score that was 10 standard errors below average, which is incredibly unlikely, you still can never reject the null for any below average score. Again, the trade-off of that would be that our region of rejection here in the tail that we predicted it in, it'd get a little bit bigger. It'd maybe move over, a notch or two. Now it's a little bit easier to reject the null. That area is a little bigger, but this area has completely disappeared. So again, we call those options one-tailed or two-tailed tests. Two-tailed tests, what's depicted here, have regions of rejection in both tails. They can detect either positive or negative differences between the means we're comparing. So it can detect any difference from that population mean we're comparing it to. The downside is that alpha level, that region of rejection, gets split in half. So the probability equals alpha divided by 2. Like I said, with alpha of 0.05, the regions of rejection will be the lowest 2.5% and the highest 2.5%. One-tailed tests, on the other hand, can detect differences only in one direction, only in the predicted direction. If your prediction is mu1 is greater than mu2, you can only reject the null if your results are in that tail. If they go the opposite of what you predicted, you can never reject the null. So you can test for either mu1 being greater than mu2 or mu1 being less than mu2. The advantage of this, even though you now have a set of differences you can't detect, the region of rejection gets a little bigger in the tail that you made your prediction in. So again, it's a little easier to do that. All of that alpha goes just in one tail of the distribution. Instead of lowest 2.5% plus highest 2.5%, it's just highest 5% overall. So which one's better? Again, I mentioned some trade-offs there. Non-directional tests are more conservative, meaning that it's harder to reject the null in that case, but they are also capable of detecting differences in either direction, so either positive or negative changes. So this is, again, a much better drawn version of my normal curve, and you can see some of the information there, 2.5%, 2.5%. And also notice we have some z-scores there. Those are what are called threshold scores. We'll talk more about them in the next couple modules. Directional tests don't change alpha, but they concentrate it in the tail that you chose, so it gets a little bit bigger. And if you look at this actual threshold score, or the numbers, the percentage here, you can see that it gets a little closer to the mean. So it's a little easier to reject the mean. So which one do we choose? Well, what we tend to do is err on the side of caution. What we tend to do in this case is we usually choose two-tailed tests. Here's the reason why. Two reasons why. One is that when in doubt, we tend to err on the side of making the null harder to reject. A threshold that's farther away will do that. Another one is that sometimes we have significant results that are the opposite of what we predicted. That's worth knowing about. If you make a prediction or you expect things to go one way, but it goes exactly the opposite way, you think your therapy is going to improve people, but it actually makes them significantly worse, you really, really want to know about that. So sometimes things coming out the opposite of what we predict is actually a lot more meaningful or interesting than coming out the way we do predict. So long story short, we tend to predict those two-tailed, or tend to use those two-tailed tests. We'll use both initially, and then it's nothing but two tails the rest of the way. So that region of rejection is what we've been talking about. Its size is determined by alpha, and it represents every difference between those means that has a probability equal to or less than alpha. Again, what we do is we figure out what the threshold or the border of that region of rejection is. So we set what's called a threshold or a critical value. A threshold or a critical value is just what's the minimum test statistic, and that's going to be z-scores early on and later some other stuff. What's the minimum test statistic you'd need to be in that region of rejection? Again, if your test stat is beyond the line for your actual sample, you reject the null. If not, you retain or fail to reject it. And here again is another chart representing how that sort of is split up. Again, the big lesson is two-tailed tests are more common, both overall and in this course. All right, that's the end. We're going to come back and talk about the process of research. Trust the process. See you then.